Hi all, today I am presenting the paper by criteria scheduling of scientific grid workflows, and this IEEE paper is written by Radi Pradhan, Marek Vigzurek, and the presenter is me, Shruti Baichpal, Department of Computer Science from Wayne State University. Let's see the abstract of this paper. First it defines the workflow, an abstract workflow, and then a grid module, and what are the criteria of that as taxonomy scheduling criteria, and then it defines the method for solving the criteria scheduling problem as an extension of multiple choice knapsack problem. And the problem can be solved using dynamic programming in two-phase scheduling algorithm, that is a DCA called a dynamic constraint algorithm, and it consists of two phases, that is primary scheduling criteria and secondary scheduling, providing through simulation and experimental analysis of scheduling approach. And then here the experiment analysis is done by comparing with two other algorithms, that is LOSS3 and BDLS algorithms. So after that it gives the real world example, that is the Austrian gate environment. I'll explain about this in the next later slides, and it gives the conclusion like how the approach has been done for the solving of the workflow in the grid model, and then using some algorithm, that is a DC algorithm, and that algorithm result will be compared with the other algorithms, and then it gives the real world example of it, and that's how it is concluded. So let's start the introduction. As I said, there are few challenges faced for the grid computing. So the drift towards new challenges in grid computing includes scientific workflow management. Here, first in the starting, there are a few approaches which are followed, and then they come for the by criteria. Let's see what are those approaches. The most common approach to the problem is to optimize only one criterion, keeping the other constraint within the fixed thresholds. This approach has an obvious limitation, since it does not allow to optimize more than one criterion at the same time. Moreover, to establish a fixed threshold is not a trivial task in the grid scheduling, because possible threshold values are usually unknown until the scheduling process is finished. And there is another common approach that faces is to linearize the problem by assigning weights to the criterion and to optimize the weighted sum. The major problem in this approach is how to define the weight properly for each particular problem, because simple linear models do not always reflect the complexity of the problem in a correct way. So then it comes for the bi-criterion scheduling algorithms, defining the secondary criterion as a sliding constraint as a function of the primary criteria. Here, if I explain like what is sliding constraint, you'll not be able to understand, so I'll be explaining this in the next slide. So just let's see for the bi-criterion scheduling historic, what they have used. They have used the algorithm called dynamic constraint algorithm, and then the simulation results for a real world heterological application executed in the Australian grid environment. So let's start with the model, how it goes and everything. Here the workflow module, it consists of two activities, that's a computational activity and the composite activity. In a computational activity, the atomic activity defines an atomic unit of computation, such as legacy sequential or parallel application, which is presented at two levels of abstractions. First, activity type and activity deployment. What does activity type does over here? The activity type is a simplified abstract description of the functionality or and semantics of an activity, such as Jacobi relaxation algorithm, a fast Fourier transformation. So the next would be activity deployment. Here what it does, it refers to an executable or a deployed web services and describe how the activity can be invoked and executed in a grid. Now let's see what is composite activity. It is a generic term for an activity that aggregates multiple activities according to one of the following three patterns, and that is parallel, sequential, and conditional. Let's see what is parallel. Here it allows user to express a large-scale workflow regions consisting of hundreds or thousands workflow regions or thousands of independent activities. Whereas for the sequential loop activity, it defines the repetitive computations with possibly unknown number of iterations. Coming to the conditional, it's like a switch or if statements that activate one of its multiple successor activities based on the evaluation of the Boolean conditions. So now let's see the next model is runtime module. Here there are like 4 types they have considered. That's a resource manager, and this is responsible for negotiation, reservation, allocation of resources, and automatic deployment of services required for executing grid applications. And for the performance prediction, this would be like estimation of an activity deployment on individual resources through an offline training phase based on well-defined experimental design followed by some regression methods. And coming for the scheduler, here it determines the workflow mappings on the grid using graph-based heuristics such as heterogeneous, earliest, finish time algorithms. Coming to the intact engine, here it is like a target scalable, reliable, and fault tolerant execution of workflows. And there is called a workflow converter, which transforms the directed graph-based scientific workflows with a dynamic structure into flat and static directed acyclic graphs of atomic activities suitable for optimized scheduling using heuristic algorithm. Let's see 2 problems, that is definition 1. Problem definition. Definition 1 would be given as a set a W, that is a workflow after directed bicyclic graph-based workflows, each of which consists of activities and a set of dependencies. Here the workflows and the T would be the set of activities and T are the dependencies. The next definition would be the cost model for the services is described by 2 scheduling criteria. For instance, by executing time and economic cost. The cost one would be workflows, and the scientific criteria with the resource, and the same for the cost too. Depending on this, it works. And these 2 problem definition can be solved by using an algorithm called TCA. And before going for that, we'll see the workflow structure, the taxonomy of scheduling criteria. Here the first would be workflow structure. What it defines? The workflow structure defines independent task. Sometimes, depending on some criteria, the workflow structure will be considered and sometimes it will be neglected. Example, when coming for the execution time, workflow structure will be considered, and if it is for the cost, it will be neglected. So there are 2 types of workflow structures, that is structure independent and structure dependent. And the next would be cost aggregation method. The cost aggregation method would be it depends on the number of criteria, like with respect to the operation used for the aggregation, and there are 3 types that can be used, that is additive, multiplicative and concave. And what is additive? That's a normal thing where a simple addition is performed to combine the individual economic cost of activities, whereas for the multiply, it will be like calculating the quality of results of a sequence of activities in a workflow, like will usually multiply the partial cost, and for coming to concave, it defines the minimum of all the costs, like finding the best solution or the bandwidth. Next would be interdependence. For this, I can give a best example of marketing, like how if you're buying if you're buying 1 shirt, it will cost you $10. If you're buying 2 shirts, it will cost you $15, and if you're buying 3, and it will cost you around $24 or $23. So depending upon the number of orders or size of the order, the cost will be reduced. In the same way, the cost of the time will vary, and these 2 criteria will be interdependence. And for the optimization direction, it's just a simple way, like increasing and decreasing of the cost. Well, coming for the interdependence, right, the interdependence depends on the criteria of the flows, such as it might be availability of the resource as a service, and sometimes it is like categorized into 2, that is interdependent and non-interdependent. The cost criteria might become the non-interdependent, whereas this execution time would become the independent. So let's come for the DC algorithm, where they've explained using some graph, and this is a very good explanation. But here what it does, it uses the 2 main phases, that is primary scheduling and the secondary scheduling. The secondary scheduling for optimizing for the secondary criteria while keeping the primary criterion cost within the defining sliding constraint. So what is the sliding constraint? It represents like how much the final solution may differ from the best solution of the primary criterion. That is how the sliding constraint is considered. So let's see the example of this graph over here. A sample scheduling processes 2 criteria, that is alpha and beta, considering both primary and secondary criteria combination. The primary solution is the outcome of the primary scheduling, and the sliding constraint delimits the maximum area to be traversed in the secondary scheduling phase. And the curved arrow shows a typical optimization curves followed by the secondary scheduling by applying a sequence of modification to the primary solution. The final solution is the point of optimization curve that optimizes the secondary criteria. So now let's see the dynamic constraint algorithm. As I said, the primary scheduling goal is to find the optimal schedule of a workflow for the primary criteria using the sliding constraint. And the secondary scheduling, like it uses the secondary criterion using MCKP, that is a multiple thing heuristic based on a dynamic approach. Here it uses the result of the sliding constraint that has obtained during the primary scheduling. And then there is memorization table, where the multiple partial solution will be stored over there, and the sliding constraint, as I said, it is equal to L, and the primary criteria cost for the solution in the table must therefore belong to the range. So let me explain about the algorithm. Here first it illustrates in the end it is storing the preliminary solution, whereas in solution final it has again stored the solution of the preliminary, but this is for the initialization. Later the solution changes at the end. I can see here in the final solution it has stored this solution, and from where this solution comes. Well, let's know by the algorithm. So here in the line 3 it is the outermost loop that gives the number of activities in the workflow, and then the 4 and 6 iterative overall partial solution which are available in the table. In the 8th line it attempts to apply all possible local modification for an activity in the given partial solution by changing mapping to all alternative services. Here the cell it initializes for the M, where J would be the size of the memorization table in the line 5th, and while coming for the line 6th, here the new solution derived from solution SO, that's given as SOL, during a single iteration of the third nested step. The next we'll see in the 11th to 19th, it gives the newly created solutions for which the total primary criteria cost is within the range. And next it explains in the final 14th to 19th, it gives the limitation and domination condition, and only if the solution is best, and that solution will be moved to the cell, and in the cell it contains a lot of partial solution, and there it will be moved. And then again it gives the condition in the 16th line, the cost of solution, total solution, by comparing with the final solution. If it is less than, then only the solution will be finalized to the final solution. That is how the algorithm goes on. There are two kinds of orders, that is activity traversal order. First would be what is the order in which the workflow activities are traversed in the outermost loop. Second would be how we define the domination relationship between two solutions. One would be domination and the complexity analysis. Here, as I said, in the 13th and the 14th line, they keep the computational effort reasonable by storing table only these solutions which are promising. In the starting, all the partial solution is moved to the cell, whereas in this line it just keep the solution which are best or final. So based on that, again it calculates. The next would be complexity. The modify condition is used in the line called 11th, that is here. I'm sorry, it's in the back line. Here in the 9th, they use the modify function to derive a new solution from the existing solution. And the next would be experimental workflows. The first run simulation experimental would be in the 3 types, that is parallel, random, and real world workflow. In the parallel, the activities of the traverse will be just a parallel one by one, and whereas in random it takes the resource and the time or whatever the criteria is, it is random in the activities. For the C-STEM, this is real world workflow. They say here, even though all the activities are being shared with the resources or everything, it has been neatly scheduled, not random. It is scheduled and the resource will be taken. And next comes for the simulation experiment, where the DC algorithm solutions are compared with the 2 more algorithms, that is LOS and BDLS. Here, what is LOS 3 applies. The loss 3 applies a local search strategy starting from a solution optimized for one criteria only, whereas BDLS is a list scheduling algorithm that schedules activities according to the priority list of activity resource space, and the order in this list is calculated based on two auxiliary priorities lists created for the two scheduling criteria. Whereas compared for the optimization process, they have just given example over here. If there are consisting hundreds of cells, and each cell will be having a 10 intermediate solution. Whereas for the optimizing progress, DC algorithm would be in the 4 bright criteria combinations. Based on that, they have explained over here. First, it might be with the time money or money time. The second would be with the time reliability or reliability of the time. And the next would be time and the data quality, and would be the data quality and the time. Next coming for the money and the data quality, and the data quality and the time. In all the things with this black color, it says the LOS, whereas the black color says the BDLS, whereas this kind of thing with the unfilled, it says about the LOS, and with the filled, with the filled triangles, as these are mapped over here, this is a DC algorithm. Everywhere you can see that DC is the highest and it gives the best solution whenever we compare with the 4 byte criteria. Here, whatever the right mark has been done, that's the best solution given by the DC algorithm. If it is in this symbol, then it says the DC algorithm is not the best solution when we compare with this criteria. The simulation experiments goes with the next 2 algorithm comparisons. The first would be like with the optimizing ratio and the scheduling time. Here it gives the better solutions for everything, but here you can see the dark line would be the DC algorithm and the loss algorithm with the light gray, whereas BDLS is completely unfilled in the graph. But everywhere you can see the DCA gives the best solution. While comparing with the next, it would be with for the different workflow sizes. Here also it gives the impact on the optimization process but affected the execution time. Here the DCA gives the best result at the expense of high computational activity or a complexity might be. And when we see in this diagram, it compare with the different workflow types. Though where the DC performs the best but has gained increased computational complexity. And the next coming for the comparison correlated and non-correlated data for the small and large resource consumption. Here first we have to get to know what is correlated and non-correlated. The non-correlated, the costs are generated randomly, whereas for the correlated, the cost values are generated to create a trade-off between the 2 criteria. That is how the difference is made, and based on these criteria, the comparison is done between LOS 3 and BDLS. Still, here the result would be best for the DC algorithm. Though sometimes when the resource consumption is large, LOS 3 is sometimes the best algorithm, and the BDLS works better when criteria costs are non-correlated. That is how it shows over here. And the next would be here the comparison of the different scheduling criteria. LOS 3 algorithm provides similar or even better result with the DCA, but then mentioned that DCA also provides a comparatively good result. That is why we always consider the DCA in all the algorithm, with the comparison of the algorithms. Here they have given the result of the real world example, that is INV mod. It is a hydrological application designed at the University of the Innsbruck for calibration of parameters. That is the water balance simulation module, a hydrological application developed at the Swiss Federal Institute of Technology, Zurich. Here it contains the very simple workflow model, even though it is not a complex, but still even here the DCA gives the better solution if we compare for this real world example. Here you can see that each iteration of outermost parallel called the random run. So a local search optimization starting from arbitrarily chosen initial solution is done. So though we know the algorithm how it works, but it always takes the random criterias, and that would be done in the outermost parallel section. But the randomly taken run will not be knowing, we just know how it is done. This is the situation when we have taken a very simple model, and think of how it does when it comes for the very big workflow module. At that time we'll not be considering the outermost parallel, how it is going through, so it goes through a random run. The next would be alternative local changes that are examined separately for each parameter to be calibrated, which might be done in parallel in the innermost section of activities. So now coming to the conclusion, we have first started some common approach for the scheduling criteria of the workflows, grid workflows. We have introduced a by criteria scheduling for the scientific grid workflows, and then presented the survey of the scheduling criteria used in existing research sets. I told two common approaches using the fixed criteria and assigning the weight to the criterias. Here again they have explained the two phases of the criteria, that is the primary scheduling and the by secondary scheduling, and they have used the sliding constraint, which would be that is the result of the primary scheduling, and that result would be used in secondary scheduling. The next would be described the by criteria scheduling problem, that is the DCA algorithm, and that the extension of multiple choice knapsack problem, and I have explained the DCA algorithm. And the result of the DCA algorithm is compared with the other two algorithms also, and where we get to know that DCA would be the best result. And real world example they have taken, and that is how they compared. And finally with this algorithm we can say DCA always gives the best solution while comparing with the other algorithms, that is LOSS3 and BDLS3. So finally, if you have any questions about this paper or any doubts, you can just comment on below this video. I'll answer all these questions. Thank you.